a Portland Community College mathematics telecourse, a course in arithmetic review, produced at Portland Community College. This tape will review our ability to change decimals to its equivalent reduced fraction. It's a very simple lesson. In fact, just this simple. It's simply a matter of saying the word name for the fraction. So the word name for this is 125 tenths, hundredths, thousandths. Say the word name and then write the fraction that you just said, and then reduce. It's just that simple. That's why we had the previous two lessons, was to review our ability to know and say what a decimal is, and that gives us the ability to write it as a fraction automatically. Then reduce, and we can see that this will divide by 5. It turns out in decimals, very frequently you'll get a decimal that ends in 25 or 75. If that ever happens, then the fraction you have will also divide by 25. 25 goes into the top 5 times, and 25 goes into the denominator 40 times. And of course, this fraction is reducible by another 5, which gives me 1/8. So this decimal and this fraction, in fact all of these for that matter, are all different ways of expressing the same number. And these two forms are the two that we are most familiar with. Okay, say the number in word name, then write the fraction with the same name. Once again, to enter into our notes or memory, to change a decimal to a fraction, read the decimal word name, write the fraction that has the same name, and reduce if possible. Now, do you see how math builds as it progresses? Each of these steps was, in fact, an entire previous lesson. And at this stage, we presume you're just automatic and accurate and fast at those previous lessons. That's why it's so very important that you do much practice problems for each lesson, just as you would on the piano or for basketball. Now, how about this problem? We know it's going to be a mixed number because it has a whole number and a fractional part. Remember, a decimal is nothing more than another way of saying or writing a fraction. So the whole number part of my mixed number is 4. Okay, now say that part. So that's 8 tenths, hundredths, thousandths. Now we have our fractional counterpart. Then it's simply a matter of reducing. Now note that the last 3 digits of that number is divisible by 8. So our divisibility test tells me that 8 will go into this, and quite obviously 8 goes into the top. 8 into the bottom is 125. And we're done. A mixed number equivalent to this decimal representation. Let's work another problem by what may at first appear like a different technique, but which logically is the same. It's a way of looking at it which is a favorite of many people. This technique simply says this: pretend like the decimal point isn't there. If it wasn't, that would be the number 85. So write 85 over 1. And of course, writing anything over 1 does not change its value. Then this technique suggests that for each decimal place, whether there's a 0 or a non-zero, for each decimal place, append a 0 behind the 1. So there are 4 decimal places. We append 4 zeros. Do not count any of the whole number, digits, or places. And that's it. Then simply reduce. Now let's check that that really is the same process logically. Say the word name, so that's 85. Then the word name, place name of the n digit, so it's tenths, hundredths, thousands, 10,000s. And that's exactly what we have. And then reduce. Okay, we can see that both of these are divisible by 5. 5 goes into 85, 17, into 10 twice, 0, 0, 0, and we're done. So a very simple technique. Once again, say the number without the decimal point, 85 over 1. For each decimal place, append a 0 and then reduce. Let's do that once more. That technique suggests that we pretend like the decimal point isn't there, write down the number that we have over 1. And then for each decimal place, see in this case 5, do not count the whole number, places. Append a 0. So we append 5 zeros. And then reduce. In this case, we can see that both top and bottom are divisible by 25. So if we wish, calculator, 475 divide by 25 is 19. And in this case, it's just as easy to divide the denominator mentally as with a calculator. 25 goes into 100, 4 times, into 0, and we're done. This illustrates a fairly good relationship between the calculator and the person doing the problem. Many people feel that because of calculators, you do less and less arithmetic. Not necessarily so. See, the calculator cannot change a decimal to a fraction. You have to do that. However, you can use the calculator to help you. So the calculator is a useful tool, but it does not replace arithmetic. Now, this matter of changing decimals to fractions occurs most frequently in technical shops, be it a welding shop, sheet metal shop, or a machine shop. In fact, it's a rare shop that does not have a conversion table between decimals and fractions. They're used that much. So let's say we've used a micrometer to measure the diameter of a metal shaft to within 1/1000th of an inch decimal-wise. And for some reason, we need to know its equivalent as a fraction. Okay, so we say the word name 825 thousandths. 825 thousandths. Once you're used to the word name, it's actually very fast. Then reduce this. We can see it divides by 5, but it also divides by 25. And at this point, if we wish to use a calculator, 825 divided by 25 is 33, and 25 goes into 104, into 0, 0. So the decimal number, 0.825, is equivalent to the reduced fraction 33/40ths. Now, if you're a little bit slippery on your arithmetic skills, we suggest that you do your reducing by hand just to check or to improve your arithmetic skills. Then check your work on the calculator, and in that manner you're improving both your hand skills and your calculator skills. We can use this lesson to prove something we said in the last lesson. Remember, we said that behind the decimal point, on the end, the right end, zeros are not necessary. On the other hand, since they're not necessary, I could even stick on more zeros, and I don't change the value. In short, we're saying that all three of these are the same number, just written differently. That the zeros tacked on to the end of decimals, the right end, doesn't change its value. Let's prove that, but let's think back on several facts we learned in the fraction chapter first. Recalling that fractions with the same value can have many forms, we notice that these three fractions are not reduced. This one in particular has top and bottom divisible by 3. So dividing top by 3 and the bottom by 3, this fraction reduces to 3/4. We notice that the second fraction is divisible top and bottom by 5. 5 goes into 15, 3, 5 goes into 24. And a third fraction, we see that top and bottom is both divisible by 7. And by dividing both, it too reduces to 3/4. So in the process of reducing these, we find in fact they're all disguised forms of the same valued number. The important point here is even though fractions might look different, if they're really equal in value, then in fact when they are reduced, they will always reduce to the same specific form, no exceptions. Now let's use that fact, that all equivalent fractions will reduce to the same reduced form, to look at our decimal situation once again. Back to these three decimals where we're claiming that the appending of zeros on the end or taking them away does not change the value. Let's write each of these in their fraction forms as they stand. So this is 35 hundredths. So I write it as such, 35 hundredths. This one, on the other hand, is 350 thousandths. And this one is 3,500. See, 10, 100 thousandths, 10 thousandths. Now let's reduce each of those three. And you can see by using our division by powers of 10 from the last chapter that I can divide both of those by 10, and indeed, even without reducing, these two are exactly the same, aren't they? And the same thing here, I can divide this one by 100, this one by 100, and they do indeed all reduce not to the lowest form, but still to a same form, so we can see that by appending these zeros, the decimals in fraction form are really the same. On the other hand, we stated that inserting a zero between non-zero digits or leaving them out does indeed change the value, even between the decimal point and digits. So end zeros, we claim, do not alter the value. Between zeros, see this is between the point and the 3, do change the value. Let's check that that in fact is true by using our fraction argument. Again, this is the number 35 hundredths, so writing it in fraction form. This is the number 305 thousandths, so writing it in fraction form. The word name for this is 35 thousandths. And these are all three fractions which are reducible. So here, dividing top and bottom by 5, I would get 7/20. Dividing this one by 5, top and bottom, I would get 61/200. Dividing this one by 5, I would get 7/200. And try as you might, neither none of these three will reduce anymore. But we stated if in fact these fractions were the same, just in disguised form, then they should ultimately reduce to the same number. But we found out they won't. So these are not the same numbers. But they came from these decimals, so these decimals cannot be the same. So do you see the insertion of in between zeros or leaving out in between zeros changes the value of decimals. So one must be very, very cautious on that point when you're writing and copying decimal numbers. So back to our main lesson, which is given a decimal form of a number, write it in its fraction form. And we had two approaches to this. One, and the fastest, if you're comfortable in word names, is simply to say this number. So this is the 28 thousandths. So we simply say it, 28 thousandths. Our second technique is, if you have difficulty with word names, is to pretend momentarily that the decimal point isn't there, then read the number, and the number is 28. But to write 28 as a fraction correctly, it would be 28 over 1. Then for each decimal place, you append a 0. And again, note, only 1 0 for each decimal place, not for the whole number places. Then, of course, to reduce this, and we can see that each of these are divisible by 4. And of course, this is the same number, isn't it? So 4 goes into here 7 times. 4 goes into here twice, 250. So again, it's fastest if you can simply say the number in word name, 28,000. Then say, write in fraction form what you just said with words. And of course, if there is a whole number portion to that decimal form, that whole number simply becomes the whole number form of a mixed number. So the whole number simply comes down unchanged. Then decimal-wise, this is 402 thousandths. So you simply say it, and then reduce. And of course, again, the whole number does not change again. And we can see that 2 will divide both the top and bottom. So that goes into the top 201 times in this case, and the bottom 500 times. And this is reduced as a mixed number now. Now, there's a special shortcut that you might use to reduce decimal numbers that have become fractions. Realize that decimals are very special fractions. They are fractions whose denominators are only powers of 10. That is, not all fractions can be written exactly as a decimal, but all decimals can be written as fractions. Let's think about that a little bit further. If I were to write this decimal in fraction form, let's see, that would be 532 ten thousandths. 532 10 thousandths. Or if you wish, 532 over 1, followed by 1, 2, 3, 4 zeros. But notice also that this denominator is a power of 10, specifically in this case 10 to the 1, 2, 3, 4th power, which is the same thing as saying that I have 4 tens being multiplied. And furthermore, and this is the important point, no matter what this decimal is, this denominator will always be a power of 10. In short, I will have nothing in the denominator but 10 times 10 times 10, either 1, 2, or many, many of them. But each 10, we can see very quickly, prime factors to 2 times 5, each one of them. So the point we're trying to make is the obvious one, that the only prime numbers that will divide the denominators derived from a decimal number are 2's and 5's. Maybe lots of 2's and lots of 5's, but only 2's and 5's. No other number will divide a decimal denominator. Well, to reduce a fraction, we want to divide both top and bottom by the same numbers. And since 2 and 5 are the only ones that will divide the bottom, they're the only ones we worry about in the top. It might be that 7 or 11 or 3 or lots of numbers will divide this. But the only ones we're concerned about are 2's and 5's. But you see, we had simple test, divisibility test for 2's and 5's, didn't we? If the n digit is even, and this is, 2 will divide it. And of course, we've just stated 2 always divides the bottom in this case. And if the n digit is 0 or 5, then we know the 5 divides it. So in short, to reduce fractions derived from decimals, you see if you can divide by 2 and 5, and you only check the top. We know that 2's and 5's will divide the bottom, and anything made up of 2's and 5's, factor-wise. Let's make a special memory note to use that. Fractions formed from decimals are only reducible by prime numbers 2 and 5. Using that fact, we can save a lot of time. First, changing it to our fraction form by whatever technique we prefer. In this case, an experienced person will be first saying it in word name and writing that word name in fraction form. So this is tenth, hundredth, thousandths, so it's 321 thousandths. Now, since I know I can divide the bottom only by 2's and 5's, that's all I check at the top. And I can see by looking at this n digit that it's not even, hence 2 won't go in. It's not 0 or 5, therefore 5 won't go in. Therefore, I'm done. It's reduced. There's nothing more. Isn't that a nice rule? Now be cautious. A common mistake for beginners is this simple one, that of simply saying the wrong word name, because there's a tendency on some to want to call this first decimal place 1 because the first whole number place is 1. But remember very, very carefully that the first decimal place is tenth, not 1. So this would be tenth, hundredth, thousandths, 10 thousandths. And of course there are 505 of them. So again, please note, never forget that the first decimal place is tenth, always and forever a tenth. So tenth, hundredth, etc. Now using the rule we just formed, we can see that this top number is divisible by 5, and of course the bottom always will be. So 5 goes into there 101, and 5 goes into the bottom 2,000 times. Now since the top number is not divisible any further by 5 or 2, this form of the fraction is certain to be reduced. Now, let's use our concluding few moments of this lesson to get ready for the next lesson. Please note 2 points. First, decimals with the same number of places will have the same power of 10's denominator as a fraction. Let's illustrate that. Now, no matter what these are as fractional values, we know that each of them has 3 decimal places. Even though this has 2 non-zero digits, this one 3, they each have 3 decimal places. And no matter what I would put on the tops, the bottom would be a 1 followed by 1, 2, 3 zeros in each case. So the point we wish to make at this moment is if the number of places are the same, before we reduce, the fractional denominators will be precisely the same. So there is a correlation between the sameness of these and the sameness of the number of decimal places. Keep that at the back of your mind as we go into the next lesson. Along with that fact, let's add this one. That is that fractions which have the same denominators are easy to order. An example in review. It is not readily discernible in this case, for instance, which of these two is the larger fraction. But as soon as we were to change them to a common denominator, which is 36 in this case, multiplying top and bottom here by 3, and top and bottom here by 2, we see that indeed they are close to being the same size, but once the denominators are the same, all we need to look at is the numerators, and since the first numerator is larger than the second, it belongs to the larger fraction. So again, these two facts will really serve us well as we begin the next lesson. That fractions which have the same denominators are easy to order, and decimals which have the same number of places will have the same denominator. In fact, let's add a third note. Appending extra zeros onto the right end of a decimal will not change its value. That is, if I have a decimal like this, and let's get several copies of them. Appending extra zeros on the end will not change it. It still is the same as it started with. In fact, I can stick on, if you will, as many zeros as I want, and the initial value does not change. 3 very simple facts. But as we move into the next lesson, it will help resolve a problem which frustrates many beginners. Therefore, keep these 3 with you until we see each other at the next lesson. Until then, this is your math host, Bob Fennell. Good luck.